All right, I'm going to start off today with how to calculate what goes on with a reaction and how much energy you can get out of it when it happens, or how much energy you've got to put into it to make it happen. Remember that G is the Gibbs free energy, and this is what we use when we have a reaction that occurs at constant temperature and constant pressure both, which are often the case in a lot of laboratory situations, so this is useful. Remember that we had a three-step process to find the change in the Gibbs free energy for our system. So first, it's going to be at constant temperature and pressure. The first thing we do is find the change in the H. H is not Helmholtz free energy. H is the enthalpy. So find the change in the enthalpy for the reaction. Then find the change in the, and we can get the enthalpy from the tables in the back of the book. Then we find the change in the entropy. So delta S. That you might find by calculating using the heat capacity, or you might get from the tables. S is in the back of the book for several materials. And then, once we've got those, we find delta G, change in the Gibbs free energy, from the relation that I finished up with at the end of the last lecture. It's the change in the enthalpy minus T delta S. So delta H is there, delta S is there, and presumably you know the temperature. That lets you find the Gibbs free energy. And once you've found the Gibbs free energy, that lets you know either how much energy you've got to put into the system to make the reaction happen, or how much energy you get out of the system if the reaction happens naturally. Remember, systems always like to go to minimize their energy state. Okay, let's see here. So, if you take a reaction and you write it out there, I'm going to give an example in just a minute. You have the initial reactants on the left, which then form the final reactants. There. Okay. You look up for each of the individual initial reactants their enthalpy of formation. Enthalpy of formation has a delta symbol in front of it already because it's how much energy it takes to make it from scratch. So it happens to have that delta there, but the delta does not mean final minus initial. The delta means to create it from scratch there. All right, so that's enthalpy of formation. You add up the enthalpy of formation for all of the initial reactants. And for the final reactants, you do the same thing. Okay. The total for the initial reactants is going to give you the initial enthalpy. And it'll be in units of, the back of the book has in kilojoules, for example, but it's really per mole. Now, enthalpy is in units of energy, not units of energy per mole. So the problems, the examples will usually say something like for 1 mole of this substance, and it goes through like that. But it's easy enough to keep track of if you have more than 1 mole. Just you can put this in sort of cheap, put it in kilojoules per mole. That's how I'll do it. You add up the final reactants enthalpies of formation, and you have the final enthalpy. In kilojoules per mole. So, to find delta H for the reaction, which is our first step, simply final minus initial. Okay. That's step 1. Step 2, you have the entropies of each of the initial reactants. I'm going to make a little more room here. Okay, so I've got, for the initial reactants, I have the entropy of the first one, plus the entropy of the second, plus the entropy of the third, so on like that. And for the final reactants, I've got the same thing. So, I add up the initial entropy, which is going to be in joules per Kelvin and per mole implicitly. I add up the final entropes. And I do the same thing. Step 2 then is change in entropy for the system. Delta S is S final minus S initial. Like I said, at the back of the book, the table that has those enthalpies of formation also has entropies for many common substances that might be useful. But you can also use the equation for S integral of Cp over T, for example. That might be a useful thing in some situations. Okay, so that's step 2. And then finally, you put those two things together. Make a little room here. Step 3 is delta G equals delta H minus T delta S. There's delta H, and there's delta S. And then you got your answer. All right, let's try an example then. So, how much energy do you need to dissociate water into hydrogen and oxygen? All right, and this example is in the book on page 152 to 153. The answer is delta G for the reaction. So our initial reactants are, well, simply H2O, that's it. The final reactants are, now, you might think we would just put H2 plus O, because we've got H2 and O. But the actual, the natural state at room temperature and atmospheric pressure is for hydrogen to be diatomic and for oxygen to be diatomic as well. And we need to put them in what their natural state would be under those standard conditions, standard temperature and pressure. So you have H2 plus, I can't put down just O2 because I don't have that many, so it's 1/2 of O2. Just put it like that there. And this is for 1 mole. Okay, again, elemental forms there. So, let's see here, how much room I've got. I think I'll put step 1 right down below. Step 1, find the change in the enthalpy, delta H, for the reaction. So I write down the enthalpy of formation, which remember already has that curious little delta in front of it. You look in the back of the book, in the table, and you'll find the enthalpy for H2O in liquid form is what? And what are the units?
Kilojoules.
All right, kilojoules and implicitly per mole. Okay, now that then is transformed into diatomic hydrogen plus 1/2 of diatomic oxygen. So what do we have for H2?
0.
0. What about for O2? 1/2 of O2.
0.
Okay. So that's pretty easy to do. 1/2 times 0 is 0. So I add up my H initial, add up my H final, which is easy enough. That's total of 0 there. The change in enthalpy, and I'm always a little bit frustrated by the presence of that delta in front of the enthalpy of formation, because then you wonder about, well, I've got a change in something. Don't worry, just change the notation here. So delta H is enthalpy of formation final minus enthalpy of formation initial. So negative 285.83 kilojoules per mole. Really, I'm doing delta H per mole here, minus 0. Well, that means my change in enthalpy is simply, oh, good grief. No. Final minus initial. 0 minus a negative 285.83 kilojoules per mole, which gets me a positive 285.83. Okay. Step 1 is done. I found the change in the system's enthalpy. Now I need to find the change in the system's entropy. Written down the reactants again. For the entropy, you can look up in the same table, H2O in liquid form, what's the entropy?
69.91.
And the units there?
Joules per Kelvin mole.
Mm-hmm. about for diatomic hydrogen?
130.68.
0.68
Yeah.
joules per Kelvin times mole, plus 1/2 times what for diatomic oxygen?
205.14.
Okay. Now, when I did the math on this, I'd actually rounded the numbers off to the nearest single digit, nearest integer. So, since I'm putting it in the full form here, if you have a calculator in, let's see what that is. So, those were all individual entropies, S colon here. Now, delta S is simply S final minus S initial, which is 130.68 plus 1/2 times 205.14.
You want the final or that added?
Give me the whole file first.
Oh, final. $163.
163.
Oh, wait.
No,
Sorry.
going to be 232, 233, something like that.
Yeah, 233.25.
233.35.
25.
Joules per Kelvin mole minus 69.91 and so the actual change in entropy is
163.34.
point what?
34.
34. Yep. Round that off and I get what I had on paper. Okay, so I've got the change in the system's entropy. So entropy and temperature together. Let me get the final step, the change in the Gibbs free energy. Using this equation here, and again, I'm really putting it in terms of all of these energies per mole. So, I'm going to, well, here and now, I'm just going to round it off, I admit. 286 kilojoules per mole minus, if we're at room temperature, 298 degrees Kelvin, and we're often rounded off to 300. I'm going to put it in 298 degrees Kelvin times change in the entropy, 163 joules per Kelvin times moles. The Kelvins go away, and I've got, hold on a second here. Yeah, this is in joules, not kilojoules, so I've got to be careful. It's one thing that they put it in what are the common or the convenient units for whatever you're looking up. But convenient units for entropy is in joules per Kelvin, but the convenient units for enthalpy tends to be in kilojoules, a lot larger. Okay, so 286 kilojoules minus, what is 298 times 163?
48,574.
48,574. So I'll put it in terms of kilojoules, so 48,000 is 48.574 kilojoules per mole. 286 minus 48, and we come up with, my math is right, 237. Okay, so delta G, maybe I should explicitly say delta G per mole is 237 kilojoules per mole. You just multiply by the number of moles on both sides to get the answer that you need. So, it scales with the size of the system. This means, in order to take 1 mole of water, roughly a handful of water, something like a cup or so, and to completely split apart all of the water molecules into hydrogen and oxygen, you've got to put in 237,000 joules. If you think about, doing this off the top of my head here, if you think about how much power that is, well, power is energy per time. So let's say we're going to use electricity to do this. That's probably the way to do it. You run an electric current through it. If you need 237,000 joules to do that, you could run in, let's say, the same power that you use for a 100-watt light bulb. A watt is a joule per second, so 100 watts would be 100 joules per second. And this would tell you how long it would take running that much current through it, that much power through it, until it was completely dissociated. If you run a higher power current through that, it would take less time. Or if you run just a tiny little trickle of power, something that would power a 40-watt light bulb, 40 joules per second, it would take a lot longer. But that's how that works. Now, a nice thing about this is the reactions can be run either way. Delta G is positive. That means that the system has to gain energy for this reaction to happen. So delta G is final minus initial, so the system gets more energy in the end than it had in the beginning. That's what you have to put in. So the system will have to have 237 kilojoules more at the end of this reaction, and it's got to come from somewhere, so that's what you put in. On the other hand, if we had looked at the formation of water from hydrogen and oxygen, so the arrow going the other way, then final minus initial would have given us a change of sign. We would have had negative 237 kilojoules per mole, which means that the system, if its change in its Gibbs free energy is negative, it loses that much energy when the reaction happens. Well, that energy, again, has to go somewhere, and it goes out into the environment, and you can capture that. So if you take hydrogen and oxygen held in separate containers, let them react, they will produce that much energy. They will give it off to the environment, and hopefully you design a system to capture that. So this is how you can, if it's cleverly done, you can generate electricity or generate heat that you can use to power an engine or whatever, if you already have hydrogen and oxygen separate. So you sometimes see, honestly, they're scam systems, but the idea of we can run a car on water. Water is basically free, therefore we can run a car free of charge. Doesn't cost anything to operate it. Using this reaction here. You could, in principle, run a car on that. If you've got hydrogen and oxygen, let them react, you will generate energy in a way that could power an engine designed for that. But what is the stable form of water found in the environment? Is it found in the water molecule, or is it found in hydrogen and oxygen separately? The stable form is the water molecule here. As you see from the fact that when these two react, they give off energy, so that favors hydrogen and oxygen already in nature having reacted to water. You do get hydrogen and oxygen separately running around out there, although keep in mind that oxygen wants to be diatomic rather than single on that. And we'll get into chemical potential later on. But if you just scoop up a bucket of water, you have to put this much energy into it to dissociate them in the first place. Then you can let them react to get that energy back. So all that a water, you might call it a water fuel cell, hydrogen oxygen fuel cell does, is it may be an efficient way to store energy that you've already put into it. So, fuel cells are not things that, unless you had some kind of a hydrogen mine, which doesn't exist, or an oxygen mine, fuel cells are not ways of generating power, they're ways of storing it. Okay. There's another example in the book which is more complicated on a, I was going to say, is it a lead acid battery? Yeah, a lead battery. And this one, it has several steps into it. I won't go in, but the basic idea runs the same way. Although an interesting note is that you have free electrons that run around in this reaction, and they're transferred from one step to another. So you've got things in terms of work per electron to move those around and generate current. Okay. Thermodynamic identities. Let me get into this. Just like we have had the thermodynamic identity, and honestly 2 or 3 versions of it, for the change in the system's energy, du, we can do the same kind of thing for the change in a system's enthalpy or free energy, or, Helmholtz free energy, or the Gibbs free energy. Okay, the thermodynamic identity for the energy, U, is du, change in the energy, for an infinitesimal change, is equal to TdS minus PdV plus mu dN, where recall that mu is the chemical potential. Now, we can derive similar relations for the other thermodynamic potentials, H, F, and G. All right, let's see here. The simplest one would be the enthalpy. Okay. The enthalpy, recall, is U plus PV. Yes, U plus PV. In fact, that's the definition of the enthalpy. So, take the differential of both sides, recalling that the pressure is presumed constant when we're dealing with enthalpy. So we've got dH equals du plus, actually here, hold on. I don't think I need to apply the presumption of constant pressure in order to do this. D parentheses PV, change in PV. There's the product rule. Just like with a full derivative, you get the same rule with a differential. So it'd be differential of the first times the second plus first times the differential of the second. So dPV is PdV plus V dt. All right, now, we've got a du in there, and we can use the normal thermodynamic identity, to get rid of du. So, let's substitute in the thermodynamic identity for du here. So that means that dH is TdS minus PdV plus mu dN plus PdV plus VdP. PdV plus VdP. Kind of hard to say without twisting your words around. All right, so put this in here. All right, now, plus PdV, this term here, plus VdP. What can I do with this right off the bat?
Cancel out the.
Right. That's the same in both places. And that's it. What I'm left with is the change in the system's enthalpy is TdS, make sure that I've kept the order I usually want here. TdS, I'm going to change the order slightly, plus VdP plus mu dN. And that is our thermodynamic identity for enthalpy. I just started off with the definition of enthalpy, took the differential on both sides, and substituted the thermodynamic identity in for du. Simplified, and that was it. Okay. Notice something here, and this is some terminology from differential calculus, but we tend to regard what this is a function of. It's whatever has the differential in front of it here. So, dH is a function of S, P, and N. Okay. As those change, the enthalpy changes. All right. Now let's take the Helmholtz free energy. I'll make a little more room. I think I got that all written in the space. Okay. The Helmholtz free energy, F. Helmholtz free energy is defined as U minus Ts. I do the same thing as before. I take the differential of both sides. I've got a product here, so I use the product rule. So I've got TdS minus S dt. What should I do next?
Substitute in the du.
Right. So I use the thermodynamic identity, substitute it in for du. So du was TdS minus PdV plus mu dN. And then I've got these two terms, minus TdS minus S dt. Now I can cancel out, let's see here, TdS minus TdS, and that's it. All right, and I'm going to arrange the order of these terms. negative S dt minus PdV plus mu dn. I tend to like having the chemical potential term be last, but I think it's only a matter of convention. Mathematically, it's all the same. Okay. And so then, dF, the change in the Helmholtz free energy, is a function of temperature, that changes it, volume, and number of particles. Something useful we can do right here is that we can make some useful derivations of other terms we've already defined in one way. For example, if, let's say, volume and number are held constant, so we have a rigid walled container and we close the system so particles can't enter or leave. Okay, those two are constant, so the only variable there is T on the right-hand side. Then, dF equals negative S dt plus 0, which means that if I solve for the entropy in terms of these, I get negative, put that negative up front, negative dF by dt. Now notice I've written it as a partial derivative. That's because I've held V and N constant. So I've got to put that in the notation. And I'll also put that down at the bottom. V and N at the bottom means that they're held constant. So you can find the entropy for a system if the volume and number are constant with this equation here. I can do that with other things too. Let's say that I've got the temperature and number constant. So I've got it in thermal contact with a reservoir. So the temperature stays the same. Closed it off so no particles enter or leave, and I simply allow it to expand or contract. Okay, then dF is, see, 0 plus, minus PdV plus 0. So my pressure becomes negative partial derivative of F, the Helmholtz free energy, with respect to volume and temperature and number held constant. Okay, anything to do with the pressure, perhaps? Finally, if temperature and volume are held constant, but the number can change, then dF is 0 plus 0 plus mu dn, which means that the chemical potential is the change in the system's Helmholtz free energy with respect to particle number at constant temperature and volume. Let's see, that's got a positive sign there. I'm going to look at one thing here in the book. Okay. We'll be doing the same thing with the chemical potential and the Gibbs free energy last. And just trying to see which of those two, the one in terms of the Gibbs free energy will wind up being a useful one for other cases. But nevertheless, notice that chemical potential is in terms of change in the system's energy of some kind or another as you add particles in, assuming you're holding things constant here. So now take a look and doing the same thing with the Gibbs free energy. Okay, so we want to see what relations we can get coming up with a thermodynamic identity for the Gibbs free energy. So, Gibbs free energy is, by definition, U minus Ts plus Pv. Take the differential of both sides. dG is du. Now we've got the product rule we have to do. So minus d of Ts becomes negative Tds minus S dt plus the differential of Pv becomes plus PdV plus VdP. All right, still got space there. Put in the thermodynamic identity for du. du is Tds minus PdV plus mu dn. And now I have these last four terms, kind of a long one. So minus Tds minus SDT plus PdV plus VdP. Let's see if that's actually all on the screen. Just barely. And now just go to town canceling out terms, TDS and negative TDS, negative PdV and PdV, and that's it. Get more cancellations at least. So, dG equals, let's see the order I want to put it in here, negative SDT plus VdP plus mu dn. All right, and this one turns out to have these handy relations for S, V, and mu. If pressure and number are held constant, then, well, pressure, how do you hold pressure constant when you're doing something? You just have the container open so that the atmosphere is pushing on it with a constant force, constant pressure. So pressure and number constant meaning you've got the system closed, no particles can enter or leave. Then dG equals negative SDT plus 0 plus 0. So S is the partial derivative of G with respect to T, negative partial G with respect to T with pressure and number held constant. If you hold temperature and number constant, then dt is 0 and dn is 0, and you get dg is v dp plus 0 plus 0. So the volume would be the partial derivative of g with respect to pressure holding temperature and number constant. And, maybe most importantly for later on, if you hold temperature and pressure constant, which of course is easy enough to do in a laboratory situation. You have an open container in thermal contact with the outside. Being open, the pressure stays constant. Being in thermal contact, the temperature stays constant. In that case, dg equals, well, dt is 0, so that's 0. dp is 0, so that term is 0, plus mu dn, leading us to a useful definition of the chemical potential in terms of the change of the system's Gibbs free energy with respect to particles at constant temperature and pressure. Meaning that, under this situation, open flask and thermal contact, for every particle you bring into the system, the chemical potential is simply how much the system's Gibbs free energy increases with every particle you bring into it. Or, in case of certain things, if it decreases, you get a negative chemical potential. So, this is how we're going to see the chemical potential drives the direction of a reaction. What if, by the way, you've got more than one species of particle? This is with respect to, well, let's assume that we only had one species there, but remember that we might have several different kinds of particles. Nota bene, note well, if there exist multiple species of particles, for example, you've got, say, hydrogen and oxygen floating around in the same container, then you replace mu dn with mu1 dn1 plus mu2 dn2 and so on, where 1 labels particle type 1, 2 labels particle type 2, and so on down the line. And then you can write that in the convenient summation. You sum over the individual particle labels. The index here, I, is just a label, up to whatever number of species you got. The chemical potential of a given species times the change in that particle species number. Okay, so in a partial derivative, if you're dealing with a partial derivative like the derivative of let's say here for volume, dg by dp with temperature and number held constant. If the number is held constant, what we're talking about in this case is the number of each individual species is held constant. In dn1 equals 0, dn2 equals 0, and so on like that. So that's what this will mean in the case of multiple species. Also, where you have the number of the particles changing. Coffee cream stain there. Okay. So if dn equals 0, you replace that with dn1 equals 0, dn2 equals 0, etc. in those partial derivatives. And where you have the number of particles changing, so for mu equals partial derivative of g with respect to n with temperature and pressure held constant, that's going to transform into a series of these. So you're going to have chemical potential of species 1 is how much the system's gives free energy changes as you add one particle of species 1 to it. dg by dn sub 1 with temperature and pressure held constant and the number of species 2 held constant and the number of species 3 held constant and so on. Then you're going to have a separate relation for the chemical potential of particle species 2. Let's say if this was for the hydrogen you've got in your system, this one might be for the oxygen you have in your system, so mu sub oxygen would be partial G with respect to the change in the number of oxygen molecules with temperature and pressure held constant and the number of hydrogen atoms held constant, so N1 constant, and anything else constant, like that. And so on.